This is question 5 from Physics 5 2005. Again, it's June, as these papers are only done in June. Your data and formula sheet gives the following equation for radioactive decay. A is equal to lambda n and A is equal to A naught e to the minus lambda t. Name the quantities represented by the following symbols in these equations. So A is the atomic mass number, A is the activity. A naught then is the initial activity. N is the number of radioactive nuclei. They'll also accept atoms there. And lambda is the decay constant. The rubidium isotope 8737 rubidium Rb decays by a single stage radioactive emission to the strontium isotope 8738 Sr. Name the particle which is emitted in this decay. So if we just write that down, 8737 Rb, and that gives you 8738 Sr. So you've taken 1 away from 38 to get 37, and you've taken nothing away from 87 to get 87, so it must be a beta minus particle. Part 2. The rubidium strontium decay is used in dating rocks containing fossil animals. At the time the rock was laid down and the fossil was formed, it is assumed the rock contained no strontium. As time passes, the rubidium in the rock decays to strontium, so that the ratio of strontium to rubidium increases continuously from 0. Determination of this ratio allows the rock to be dated. When a rock containing a certain fossil is sampled, it is found that the rubidium content had dropped from 100% to 87.27%. Calculate the age of the fossil. And it gives you the half-life of rubidium is 4.75 by 10 to the 10 years. So I'm just going to do a wee calculation here at the side to work out lambda. Lambda is 0.693 divided by the half-life. Now, since we're working out a time, and our time can be in years, I'm just going to leave the half-life in years. And so that's going to be the value of your decay constant, and it's in years to the minus 1. Okay, so then you're going to put that into your equation. The equation we're going to use is equal to n is equal to n naught e to the minus lambda t. And we know that the number of radioactive nuclei at the beginning should be 100% of rubidium, and then it has dropped to 98.27. So we have to put those into decimals. And so now what we have is 0.9827 of n naught. That's what we now have. So n is equal to, if I write that over the side as well, 0.9827 of what it started out to be, n naught in other words. And that's what I'm going to put into the equation. 0.9827 n naught is equal to n naught e to the minus, and then I'm just going to write a bracket here, and that bracket is that number up here, which I haven't worked out, times t. So then naughts cancel out, and if you take log of both sides, you have the log of 0.9827, and that's equal to, you've got rid of the e, and that's equal to minus this number. The lambda number has worked out to be 1.459 by 10 to the minus 11, and that's times the time that we need. So we're now getting a sum here that we can deal with. So we've taken log of both sides, that gets rid of e here, you have to take the natural log of this here. That number in the bracket was this calculation up here, and that number works out to be 1.459 by 10 to the minus 11. So the time then is going to come out as, when you do your calculation, 1.2 by 10 to the 9 years. 1.2 by 10 to the 9 is your final answer. Nuclei of atom can exist in excited states. When an excited nucleus returns to its state of lowest energy, the ground state, a gamma ray photon may be emitted. The mass of a cobalt atom, where the nucleus is in its ground state, is 59.9308 units. The energy of the gamma ray photon emitted when this nucleus returns from its excited state to the ground state is 2.13 by 10 to the minus 13. Calculate the mass of the atom when the nucleus is in an excited state. Give your answer in units. So the excess energy emitted is equal to the mass lost. And we use E equals mc squared. So I could just write E equals mc squared. So we're looking for a mass. We're going to change that equation around. Is equal to E over c squared. And the E that we're using is the 2.13 by 10 to the minus 13. And of course, c is 3 by 10 to the 8 squared. So that answer comes out to be 2.367 by 10 to the minus 30 kilograms. Right, but 1 unit is equal to 1.66 by 10 to the minus 27 kilograms, and that's in your data sheet. Therefore, that calculation in kilograms divided by 1.66 by 10 to the minus 27 is the same as 0.0014 units. So the original mass then is equal to the 59.9308 units plus that mass that has been lost. And the answer then comes out to be 59.9322.